Thank you, Dahlia. I appreciate that. So let me recapitulate. It'll only take a moment. So welcome. We are discussing 3.2 measures of variation, and we are trying to look at how does a data set vary. That's V-A-R-Y, vary. If I had a data set of 666, no comments, the mean is 6, and there is no variation whatsoever. On the other hand, if I have a data set of 3, 6, and 9, the mean is 2, 6, but I've got some variation, and the question really is how much. 1, 6, and 11, still the same mean, but even more variation. So for those of you just joining us, which is an interesting way to work in the fact that I forgot to turn on the recording button, we'll just jump into the formula. Standard deviation is your basic measure of data spread. We have two flavors, one for a sample and one for a population. The sample, S, gets the normal everyday Arabic, if you will, notation, alphabet. Populations usually use the Greek alphabet when we talk about their parameters, so sigma for population. We've got a couple of formulas here. And let me emphasize, I do not expect students to use these formulas. They're here for us to marvel at them and understand how they work and realize that there's a bit of difference between their denominators. We make an adjustment when we work with a sample standard deviation versus a population standard deviation. And the reason for that has to do with some deep mathematics right here that I will not go into. So there we are, standard deviation. That's where we begin our discussion on measures of variation. So we'll begin my example with data from a sample. In this case, I like speeds in miles per hour. Why? Everyone understands speed. We've all had a ticket or two, 3 or 4, maybe if you were me. And we've got a sample. Oh, let's look at something reasonable. Let's look at something like n equals 5. I want the first example to be very reasonable because eventually I'm going to come back here and talk about that ugly formula. So here are my 5 speeds. It's a simple random sample for all intents. And there we go. So 1, 2, 3, 4, 5. So I'm going to jump over to my calculator right now and run through the keystrokes for finding the standard deviation. Now, if you missed last night's lecture, don't worry, it's recorded and I do believe it's available. Also, I'm going to go through the same set of keystrokes right now. I do this a lot during the semester. You really can't see this stuff too much. You can't practice it too much. My son just got back from parkour and he's been jumping around like crazy. I'm going to turn my stat wizard off. Always bothers me. Okay, so if you were not here last night, I'm going to go through the process of entering in your data again. I go to the stat key. First drop-down menu is edit, which is the one I want. I am going to use list 1. I don't want those numbers anymore, so I scroll up to the name, and you can actually see the values listed. I hit clear, followed by enter. And again, these keystrokes are available in any number of places in your Canvas course shell. So 65, 63, 79, 81, and 52. So my data is in there. Because I have a difference in my formulas between samples and populations, that denominator is fundamentally different. I really need to make sure that I know what I'm working with. I'm working with, oh dear, hold on. There we go. Sorry about that. Let me try this again. All right. So let me just go through that again. I clear and I hit enter and we're done. All right, so we go in with the 65, 63, 79, 81, and 52. So my data gets in there. And once my data does live in there, then I can go ahead and start to use it. So as I said, the keystrokes for finding things like the mean and the median and the standard deviation are the same. So stat, I scroll over to calculate. I select the one variable stats, and I point it at the list where my data lives. I hit the second key, which gives me access to the blue stuff. So number one is L1, which is where my data lives. I blow on it once for luck, and I hit enter. So we see a couple of things there. In fact, we see a whole bunch of things there. The first number is the mean. I'm not after that right now. What I'm after is the standard deviation. Your calculator butchers the notation. It annoys me no end, but we've got to live with it. My first number here, SX, that's not sex, it's SX. It's actually an S, and it should be a lowercase s. That's my standard deviation there, 12.0415 and change. Right below, I see my population standard deviation. And you'll note that it's a very different number. I need to know whether the data comes from a sample or a population. If it comes from a sample, I take the first number. If it comes from a population, I take the second number. I've got to read the problem to know. It's not obvious which one to take unless you read the problem. Look for the word either sample or population. There's other stuff down there, things like the median for last night's lecture, but right now I'm interested in the standard deviation, S. All right, so that's my standard deviation. I'm going to stop my sharing right now and come back to my screen. And I will note my standard deviation. S equals 12.0 miles per hour, because those are the units. If you were not here last night, we insist upon notation, rounding, and units. Those are the three things we insist upon when we report various sample statistics. So there we go. So the first of our measures of variation is a standard deviation. And my second measure is what we call variance. The next measure of variance or variation, excuse me, up for inspection is what we call the variance. Now, this is where things get a little funky for students because of what's going to follow. Sometimes it proceeds, and I think that's why the issue is. The variance at the end of the day is literally just the square of the standard deviation, which reminds me, I made an error on my formula back here. Ah, what a sophomore error. I'm going to bring this screen back up here. Yeah, it ain't right without the square roots. You'll find these formulas. You'll find these formulas in the lecture summary and technical detail. I cannot emphasize enough that our calculator is the way we go about using these formulas. So the variance is the square of the standard deviation. And this is where I was wrong before. So it's what we had up there on the other screen, and I apologize for that. Squared. There we go. Mu, because we've got a population over here, just and downstairs. By the way, this is a population finite correction factor or words to that effect, which is why we put that in there. If you really want to figure out why we need a population correction factor, you will take an advanced course in statistics. So the variance is literally the square of the standard deviation. And this is really the first time I think that we encounter an issue where we really need our calculator's help. So let me go back to that last example where we have a sample in miles per hour that we just got done looking at. It's already in our calculators. 65, 63, 79, 81, and 52. So I've got my variance, S squared equals, and sigma squared equals. So I'm going to go through these keystrokes a couple of different times over the course of the next few days, because it's truly one of the first times we've really got to use our calculators on a, if you hear noise in the background, it's apparently the Giants just hit yet another home run. So as I say, let's come back to my data. Let me share my screen. All right, so there's my screen. Supposing we had to start from the very beginning, there is my data set. Stat, calculate. One variable stats, second L1, and you hit enter and it brings it all back again. It's really easy to bring this stuff back again if you forget to get something. So I see my standard deviation for my sample and my population, but I do not see my variance. And this is one of the few times that rounding really matters. So the variance is the standard deviation squared. I need to make sure when I calculate that standard deviation that I do not use a rounded value. I want to use every decimal place my calculator has, otherwise I could be off by a rather significant amount. So, and by the way, these keystrokes are in our videos. If I need to take a standard deviation, either one of those little puppies, and square them, these are the keystrokes I use. Here is the vars key. Vars is short for variables. Your calculator does try to help. By the way, the Zoom has nothing at all to do with the meeting. Look at option number 5, statistics. That's the class we're taking. So if I want my sample standard deviation, she's right there. I hit enter. It doesn't look impressive, but it's all there. If I really want to see all the decimal places, I hit enter one more time and they're all there. Vars, statistics, sample standard deviation, and then I hit the X squared key. So it's going to take that 12.04 and change and square that. I don't have to worry about punching in all those numbers accurately. My calculator remembers much better than I ever will. You too. So I hit enter. There we go. and I get 145. Bingo. If I need the population, variance, vars, statistics, sigma, square, enter. So I'm going to go ahead and stop my share and switch back to my problem set here. And I will note that my variance is 145 for the sample. Ooh, but we squared this, so we've also got to square the units. 145 square miles per hour. There should be an H in there. There we go. 116 square miles per hour. You'll note the square. That's because we have to square the formula for the standard deviation. That gets rid of that square root you saw on the previous screen. So we now have the standard deviation, the variance, and there is a single measure of center, or excuse me, variation left to go. It is called the range. And the range is literally just the difference between literally a simple difference between the minimum and maximum values. So the range, and there's no different formulas for population standard deviation here. It's literally just max minus min. So if I bring back that data set one last time, I find the biggest and the smallest numbers. My range, literally 81 minus 52, whatever that little number might be. 81 minus 51 would be 30, minus 52 would be one more than that, or 29.0 miles per hour. We'll talk about rounding in just a moment here. But there we have it. We have three measures of variation. We have standard deviation, which is used most often in the first part of the course. We have the variance, which is the square of the standard deviation. Then we have the range. All of them play a role. The variance in particular turns out to be quite important in more advanced statistical analysis. And we'll see just a wee bit of that at the very end of the semester. So we've looked at our centers of variation, or excuse me, our measures of center and our measures of variation. There's one last thing I want to talk about regarding the topics from 3.2. This was going to play some rather significant role in our discussion as we go forward this semester. I think it's frozen. Oh, never mind. Are you going to record this meeting? Yes, I did start. Yes, I did. And by the way, I hope people have been able to find the recordings of our office hour meetings. They are in the Canvas course shell. Hopefully they are sufficiently marked that you can find them. All right. I'm going to introduce this notion by asking a question is, when is a data point far from others? We've had a rather basic discussion on the notion of outliers. This notion of when a data point is far from others really turns out to be super, super important. And it takes a couple of different forms as we go through the semester. But when is a data point far enough from other data points that we can say, oh, that guy is out there? And there's a number of ways to do that, by the way, but we do have some rather fundamental ways of going about that at this level. So we have what we call the range rule of thumb. Thumb, yes, like, my thumb. Anytime you see that range rule of thumb, or I should say the phrase rule of thumb, you should note that it's a rather generic sort of statement, and it might be different someplace else. So the range rule of thumb says the following: scores at least 2 standard deviations above or below the mean are either significantly high or low. So this enables us to figure out what some value is in some sense out of line with everything else. Let me give you an example of that. I'll give you the generic stuff first with the formula for a sample. If we put stuff on a number line, and I've got my X bar in the middle, there's one S, there's two S's above the mean, there's one S, there's two S's below the mean. The stuff out there, including this data point right there, is significantly high. The stuff out there is significantly low. The 2 standard deviations is a rather arbitrary number. Why did you pick 2, not 1, not 3, not 2.5? But it's what we use. That's why it's a rule of thumb. So for our sample, we use X bar plus or minus 2S. For our population, very similar picture. We have mu for the mean, sigma for the standard deviation. It's 2 steps of sigma up, 2 steps of sigma down, high and low. Where we say significantly, either high or low. It's kind of like a grading sort of thing. Now, let me give you an example of this. By the way, all this detail is really rather extensively described in your, I believe it's chapter, lecture, summary, and technical detail. So, IQ. Population-wise, we have a mean of about 100 and a standard deviation of 15. So, if I put that on a scale, we got 100 essentially right in the middle, and I take steps of 15 up, 2 of them. 15 and 15 is 30. So we've got 130 there. Steps of 15, 2 of them on the way down. I've got 70 there. The data points or the IQs that are 130 or greater are what we say greater than or equal to 130. Similarly, at the other end of the spectrum, and by the way, this is how we figure out who has true special needs. We have significantly low when we are less than or equal to 70 IQ points. So we have this notion of the range rule of thumb, and it really plays a big role in our analysis as we get further on into inferential statistics. For now, it's just a way to identify scores that are either significantly high or significantly low. It's important to remember that the level of significance does include the actual endpoint there after you've taken your mean plus or minus 2 sigma. In this case, it's 100 plus or minus 2 times 15. And this is a way to identify when something is out of kilter with a mean or perhaps an assumed mean, whatever the case might be. All right, let me see. Are there any more questions in chat? No, nothing new. So let me go ahead and leave this screen. Return to my home screen. So there we go. That's my discussion on measures of variation. I'm not sure it's really obvious, but I've taught this class for a long time. And honestly, it took a while for me really to come to a deep appreciation for the need for both a measure of center and a measure of variation. How things clump together and how they're spread out are two very important components of any sort of data analysis. You can't go anywhere without knowing that type of detail. There we are. Are there any questions? Raise your hand, throw something into chat. I see nothing there in chat. You know, if there are no questions, I'm done with my lecture for tonight and I shall let
Wait,
you.
I have a question.
Oh, Dahlia.
Yeah. So tomorrow, are you going to be talking about the same thing or?
No, tomorrow I will talk a bit about 3.3 measures of variation. And then I think at some point I'll probably go back and try to tie 3.1, 2, and 3 together.
Okay. So like,